Thank you so much. And I will say that I am traditionally very bad with microphones. So if I wander away in the back, just give me a wave and I will get myself right back here. So as Karen Deep's sort of description of how I got here, it's been a little bit of a rocky road, not rocky road, wandering road. But even whenever I reflect on it, what I try to remember is that even when I was over in the Dana building at the at the time it was the School of Natural Resources and Environment, but I just learned that they changed their name more recently. Those conversations actually are very similar to the conversations that we were having here. And that was actually really exciting to see that in Midas, some of the environment school folks are in that group as well. Because the conversations we were having there and here, the theme is that there's so much that we can learn from data often that we're already collecting to improve and empower both individuals and communities. And there our work was much more about community health. But that theme continues. And here, where I'm talking about that, it's this idea that models are not static. Our world is constantly changing. I mean, we just talked about how quickly the AI world has changed. And so if we're going to deploy AI responsibly, we need to do that and think about it in this learning context with learning prediction systems. So before, we were just so excited to have a lot of data, and we just built a ton of models because we could, and it was exciting. And for a lot of health outcomes, we built hundreds of models, and for very good reasons, most of those went nowhere. And that work just was more publications for more people. We are starting to plug up a lot of these holes because we're thinking more carefully about how we design our tools to make them useful and make them actually helpful in guiding actions that we might make different choices in treatment or different diagnoses. And so we're starting to move towards implementation, and that's really great. And as we're more carefully designing those implementations, we're actually hopefully getting some real adoption. But there's a lot of challenges to that even as we do better in our designing of tools. And that's because generalizability is very hard. We all know that, right? You build a model in one population, it's not going to work that well if you take it somewhere else and the patients are just completely different in terms of their risk factors and distributions. You build a model in an urban area and you want to apply it in a small rural community where they have different exposures and different access to care. It just doesn't work well. You build something in an academical medical center like here, it might not work well at the small community hospital down the road. And then the piece of generalizability that I tend to focus on is this temporal generalizability, which is you build it today, you test it today, it's not necessarily going to work tomorrow or 6 months or a year down the road. And so some of the folks over at the University of Manchester who do some really good methods work around clinical prediction last year came out with this commentary that said there's no such thing as a validated prediction model. And I think that's a pretty hot take. I would take a little bit of a more hopeful approach. Their point is very well made. Generalizability is very hard. But I would say it's fickle and fleeting, but there are things we can do to promote that performance over time. It's not all bad. So the reason temporal generalizability is hard is that it's not just that we move models from one place to another, it's that even if we check them for our system is not the same today as it is tomorrow. And I think that the pandemic really highlighted this for many of us in a really stark way, but even when things are a little less hectic and crazy, we're still seeing change over time. So our populations change either because our communities are evolving or because our health system is buying up smaller hospitals and changing the catchment of who we're actually treating. The way that we understand disease and the treatments that are available change, and that could change how well a model might be able to predict. And then even just the way that we capture data constantly changes and impacts our models in unexpected ways. So we get a new lab system or a new imaging system that changes the precision and the accuracy with which we're capturing data. That can change how well the patterns that we previously learned actually work on those new patients. And the first really well documented example of how these temporal changes impact clinical prediction models came from the Euroscore. So this was built on data from the late 1990s across a number of European countries, and they were trying to predict mortality after cardiac surgery. And what they found after a few years was they were getting a lot of complaints that the model was really over-predicting how the likelihood that a particular patient, am I not? Yeah, I'm sorry. No, it's okay. I'm never loud enough. You're fine. that better? Oh, I can hear myself very loudly.
There you go. All right.
Okay, perfect. Thank you. Thank you so much. And so the Euro score, they got all these complaints that it was predicting really high probabilities of mortality for patients that they just knew were not at that high of a risk. And so they pulled together a lot of data over almost 10 years that the score had been available, and what they found was that performance was deteriorating over that time. The rate of mortality was declining, but patients were actually looking riskier, and so the model was predicting higher and higher probabilities. And I just want to quickly, while I have this slide up, because I was just in a room where the speaker and the audience had very disconnected understanding of what plots we were looking at. This is a calibration plot on the right. And so if you're traditionally used to looking at discrimination plots of the ROC, you're going to say that diagonal line is a terrible idea. You don't want to be there. But in a calibration plot, which is the predicted probability versus the actual event rate, that diagonal line is exactly where you want to be. And so if you are making that disconnection, it can be very confusing and have very difficult conversations going on. So here, that line, you can see over time that calibration curve was pulling farther and farther from that ideal line, which is not what they wanted to see. And so in response, they went ahead and just rebuilt the model, which is absolutely a valid choice. We looked at this and said, well, you know, the Euro score is just a logistic model. At the time, we were all very excited about machine learning and AI. Maybe if we used a better learning algorithm that captured all that complexity and interactions and nonlinearity, maybe we wouldn't have this problem, right? Maybe the model would just be more stable. And so we went and grabbed data from the VA. So we had a national data set, lots of data over 8 or 9 years, and we predicted 30-day mortality after inpatient stay, and then separately predicted hospital-acquired acute kidney injury. And so we used 1 year of data and trained a number of different algorithms on that 1 year of data, and then applied those algorithms on the subsequent years. So all of the learning algorithms had the same information available to them, and then they were applied over the same patients moving forward. And what we found is that while the patterns of drift look different, so here this is a calibration index, how far that curve is from that ideal line. So lower values are always going to be better in a lot of the plots that I'm going to show. And so all of the algorithms were susceptible to drift, but what that drift looked like and when it happened and the trajectory varied across the learning algorithms, which really highlighted for us that there's not sort of a one-size-fits-all to think about how we maintain our models, but they're all going to need us to pay attention to how well they're doing over time. Temporal generalizability is not going to be solved necessarily by just having more complex models. And this drift can have real implications. So, you know, we all actually have experienced this in our own lives in various tools that we use every day that suddenly just don't work well for us. You know, but if I turn on Netflix one day and the algorithm is presenting me with just ridiculous shows that I am not interested in watching, that's frustrating because I have to filter through all that content, but it's not a safety issue. In healthcare, it really is a safety issue if our models, the behavior changes unexpectedly, either gradually or rapidly. And I don't know that I have to make that case here as much as I would have to make it other places, because at Michigan, you have what I think is a really good example and a really well-documented example of how sudden changes in the performance of a model, here for that sepsis model that started flagging and alerting just all the time during the pandemic, where you actually turned it off in April, I believe, pretty quickly, because the environment was changing, right? It's working in a different place and it has to perform differently. And so the utility of those models changes very rapidly, the impact, and that can be a safety issue, but it's also a trust issue. We ask people, our patients and our providers, to trust these models and integrate them into their decision-making process, and then suddenly we're providing them with just really different information that's not adhering to what we promised. That's a problem. And so responsible and ethical deployment of clinical prediction models are really going to require that we have this ongoing monitoring and maintenance, and that we sustain those models over time. And so back in 2019, the National Academy of Medicine integrated that into their life cycle for clinical AI by adding a piece that's, even if you have successful implementation, you're not done. You've got to monitor and maintain your models. So, but we didn't have a lot of guidance to do that, and we're not actively doing that in a lot of contexts yet. And I will also mention just here that while I tend to talk about analytic AI models and prediction tools, because that's where we've been working on this, we already have evidence that generative models also drift over time, and we don't have that well characterized yet. So a lot of these issues we're going to have to address in that space as well. So what have we done to fix this problem? So as I mentioned, the Euroscore, they were like, hey, it's not working well. What are we going to do? And they just built a new model. They just trained a new model on that more recent data. And now they are currently working on collecting data for Euroscore 3. It's been another 10 years. So that model has probably drifted again, but now we're finally collecting data. So it's very reactionary. And there's probably something better that we can do. The other approach that tends to be a little bit more proactive, but is also not informed by what's going on around it, is this idea of, well, maybe on a scheduled basis, we'll just retrain our model on recent data. And that's what's been done by the National Surgical Quality Improvement Program. Their risk adjustment model, they just rebuild it every 6 months using the past 12 months of data, and they've done that for over 10 years. So they're trying to keep it up to date, but there's no reason to assume that every 6 months it needs that work, right? Or that a year of data is the right data to make that choice with. And so there might be something better that we can do. We were very concerned that, retraining, you're susceptible to overfitting. You're ignoring everything you already learned in the previous model that you built, right? So is that really the right approach? So we went, and I'm going to use the mortality models from our VA analysis earlier, just as a kind of, we're going to keep coming back to the same plots to make it easier to kind of think through. And so here we have the performance over time for just a couple of the models. And the yellow line is if we just retrain them every year on the last 12 months of data. And what we found is that for some of those models, yes, we improved calibration, we got that line down lower, closer to 0, and it was more stable. But for other models, retraining every year not only didn't improve performance compared to the original model, but some years it actually was worse. And that's definitely not what we want to be doing when we're trying to sustain models if we suddenly make them worse unexpectedly. And so annual retraining doesn't seem like the best, most informed approach that we can do. And so we wanted to take a more learning prediction approach where we and we did not coin this term, I would love to say we did, but Richard Riley and his group did. So this idea that we can actually grow right out of the idea of a learning health system and create a learning prediction system where we're getting all that feedback on how our models are doing, and we're using that to iteratively improve the models that we're delivering and guide that evolution with the data. And so the key questions that learning prediction systems have is this idea of, well, when is it just noise and variability, or when has performance actually deteriorated? How do we distinguish those? What data should we be using to update, if not always a year, if we want to make more informed choices? And then if retraining our model is not the way to go, what should we be doing, and how should we be thinking about that? And in all of these cases, because we know that different learning algorithms are going to be experiencing different things, my personal preference is that I think calibration is really important, and if you can sustain that, that feeds into all other performance metrics. But maybe for your use case, you're not interested in calibration and you want to do something else. Great. We need these to be really generalizable, regardless of how the model was developed or what aspects you want to be sustaining. So our team came up with this surveillance framework for data-driven monitoring and maintenance, and I'll kind of walk us through it quickly, but it's focused on calibration in our implementation, but it's designed for you to be able to swap out pieces and focus on the aspects of performance that you're most interested in. So let's say we have a prediction model, and it's delivering predictions for our clinical application. In the background, though, we can collect those predictions, collect those outcomes, and then in an ongoing way monitor, in our case, calibration, or whatever metric you want to monitor. And then we can use drift detection methods typically those are coming out of the statistical process control communities research, to say when has the distribution of our error, of our whatever error metric we're tracking, when has that changed? And hopefully use a drift detection method that's going to inform not just, hey, something's changed, you should update your model, but give us some insight into when did that change start, what data might be most useful for training the model. Because if we use data from the old context, we're not going to get the best performance on those next patients. We want to use data from this new context. And then feed that into some kind of a statistical test that tells us, how do I pick what updating method to apply, and then we get the new model and we keep going. So I'm actually going to start with the test for what update you should apply, because that really helped inform us and guide us to say, when we update is also really important. So I mentioned before that retraining is not always the way to go. There's a lot of things that we can do. Some of them are really simple. Sometimes we don't want to change anything because we can't do better than we currently are doing given the data we have. But there's also a number of variations of recalibration where I can just adjust that prediction a little bit to get it closer to the line. And so recalibration is actually relatively simple and doesn't require all that much data to do. And then, of course, we can retrain or we can even revise the model. So all of those need to be available to us to make sure that we can get those models back into use. And so picking between them, it would be helpful if we had some guidance. So we want that guidance. When we were thinking about how to do that, we wanted to make sure that let's change the model as little as possible. Let's prefer minimal adaptation so that we're not just constantly doing the biggest thing, partly because we want to avoid overfitting, and partly because it's just for transparency and the comfort of our users. If we can promise them we're going to change the model as little as we need to, but to meet your expectations, that's just a little bit reassuring. So I'm not going to go into all the details of the test that we designed, but it's focused around this idea that we don't want to overfit when we're training our updates, but we also want to account for uncertainty. So even if we control for overfitting, if we have a very small updating sample, we want to make sure that it generalizes not just to the updating sample, but to those next patients that arrive for as long as we hopefully can. And so we wanted to account for the sample size and that uncertainty in our decision-making process. So for this test, if you can give it a ranked order of how you prefer updating to be considered, give it a training data set, whatever metric you want to optimize on. I recommend the Breyer score because it's balancing discrimination and calibration. Then what it's going to do is find the updating method that performs best, and then it's going to say, is there anything simpler I can do that's not statistically different than that best performing update? Because I just am going to recommend the simplest thing that doesn't compromise performance. And so when we apply this in simulated data and in some real-world data, what we find is that it does pretty well. If we give it enough data, let's say we gave it a year of data, it consistently picks the method that performs best on that next data that arrived. So in the window right after updating, it did pick the best method. But if you don't give it a lot of data, it errs on the side of caution. And that's how we built it and what we wanted. So if there's not a lot of data, it will pick a simpler updating method and sometimes lose a little bit of the performance that you could have achieved. But it's trying to do that by avoiding making undue promises. So we had that. And we went back, now if we go back to our 30-day mortality example, what we see is that if we applied that every year, so here, parallel to that annual retraining, we're just going to apply our test every year, use 12 months of data. What we found is we get this green line, lower down again towards 0, which is what we want. So we got more stable, better calibration. That was exciting. But these little dotted lines show that even though we applied the test every single year, it actually only told us to do anything a couple times. And most of those are recalibrations. One of them for the random forest is a refit. But other than that, it's just doing little bits of recalibration, and it's not doing it very often. So this reminded us that, if you have a lot of models, we shouldn't be running tests to check on models that are doing fine, right? So we really need to guide when we actually even bother to consider whether or not we want to update. And so we wanted to monitor in our system that a calibration curve, because that's going to give us a sense of, along the whole spectrum of probability, how are we doing? How well are we aligned? And so the reality is a calibration curve is just a logistic regression with whatever parameterization we want to put in there. And so we didn't want to refit that calibration, that logistic regression, every time we get new data, because then we have to make just unguided assumptions about how much data to put into the curve, right? And we're trying to avoid making assumptions about the speed of drift. So we used a continuous learning or online learning approach and said, well, if we have these logistic regressions, we can create dynamic calibration curves by just integrating the error each time and moving that curve in response to changing patterns of error. So if we have a model that's well calibrated, like say the gray dotted line that's reflected by the red calibration curve, that's where we start. And then suddenly we start having predictions that are from a different calibration context, here shown by the dotted black line. What we find is that very quickly the curve starts migrating towards that new calibration setup, which is exactly what we want to see. Now, you'll notice up in the higher probabilities, it did not migrate very well. And that's partly because we tend not to have a lot of data up there, so that's probably okay, right? We need to be calibrated to where our data falls, and we're not going to do a good job learning where there's not a lot of data. So that's why you're seeing that up there. But so we're able to get these curves to evolve to reflect the new calibration context. But when has that changed enough that we need to do anything, right? That's still a problem. And so for that, we used drift detection using adaptive windowing, or ADWIN. So what ADWIN does is it takes some time series of an error metric, whatever you want it to be. In our case, we use the distance between whatever our current calibration curve was and the current prediction at the probability of the prediction. So where the current prediction falls, what's the deviation of the curve? And we tracked that over time. And what it does then is say, I don't want to decide ahead of time, this is the sliding window that I want to consider for changes. Adaptive windowing actually looks at multiple cut points between new and old data, and then tries to find a cut point where there's a difference in the error distribution between those two windows. And so if it finds a difference in the error distribution, it's going to flag and say, hey, drift, I noticed there's an error change. But it's also going to return whatever window it considered to be recent data that looked different. And so if that recent data looks different than where we were, maybe that can guide our updating process. And they'd shown in the original study where they designed ADWIN that it can handle abrupt change, it can handle gradual change, and really it can handle any error metric that is bounded. So it's very flexible and can be used across different performance metrics that we might want to consider, even if it's not this calibration deviation. So in simulation studies where we went from calibrated to a whole variety of different types of miscalibration, and we did it quickly or abruptly or very gradually or seasonally, what we found was that this is a pretty dense plot. But if you look at the orange whisker plot along the bottom, that's the distribution of detection points. And so we had very few false positives. The system tended to flag that drift was happening after the simulated drift actually did happen. So that's reassuring. And the green box represents the median window that was returned. And those are also after that red line of where drift started. So it was, in fact, giving us data that reflected that new calibration context. So that gave us the methods we needed to support this whole sort of surveillance-based approach to driving model monitoring and maintenance. So if we go back to that, again, this is that same 30-day mortality model, just for ease of looking at things. What we found is that applying that whole system together, we were able to keep that calibration better and more stable with very few interventions. And if your vision is better than mine and you look very closely, you'll notice that those change points, those dotted red lines, are not aligned with the calendar, right? When it wanted to do something was not driven by the arbitrary when we decided it's January 1st. And if we had instead made choices that aligned with the calendar, we might have really long interim periods of a model that isn't doing well, right? And this way we're able to better align changes with when the actual change is happening. And we don't have to know ahead of time what we think might be changing, because oftentimes we don't know what's changing, or we can't predict that it's going to happen. So around the time that we had these methods come together, there was a group of researchers, Jeremiah Brown at Dartmouth, Michael Matheny at Vanderbilt, and then Richard Solomon at University of Vermont, who were putting together a control trial looking at a quality improvement project to reduce AKI after cardiac catheterization at a number of VA sites. And one of the interventions they wanted to do was it involved a dashboard that provided each site with risk-adjusted insight into how well they were doing over time and compared to regionally and nationally how well, whether or not their AKI outcomes made sense given the patient population that they were seeing. And we were having all these discussions about, well, that's great, but if you're not maintaining the national model, then the insight within those dashboards might not be helpful in helping them know, are we doing well? Is what we're doing working, or do we need to take some more steps to try to improve our quality? And so we went back to look at if we had pulled the data from when the model that they were starting with had originally been built up through right before the trial was going to start. We pulled all of the catheterizations at the VA. And we looked at the model's performance, and it was significantly over predicting risk, right? We had here we're looking at ODE, because that's the metric that for those quality dashboards was most insightful for the sites. And if we applied our surveillance updates, we were able to, over that time period, over those 6 years, get to a more calibrated model that was pretty stable. And if we could keep the national model stabilized, then changes that local sites might see would be more informative to them about how well they're either improving or struggling with their outcomes. And what we found, we actually looked at VISNs, which are Veterans Integrated Service Networks, rather than local sites, because we didn't want to confuse the actual sites that would be part of the trial. And there's 18 VISNs, and they're generally geographic, but technically they're administrative, so some of them are not geographically connected. And what we tended to find was the top plot, where the original model would have told them, you're doing better than expected, you have great outcomes, when in fact they were doing fine. So those are not terrible ideas, but we don't want to overpromise, but they were doing fine. The more concerning problem that we would have had if we weren't maintaining the model we found in the bottom two plots, where there were regions that the model was just overly optimistic, and when it would have told them, you're doing fine, you're doing as expected, your outcomes reflect what we expect for your patient populations, when in fact, for most years, they were having more AKI than we would have expected. Sometimes these ODEs were as high as 1.5, and that just wouldn't have been shown to them if we weren't maintaining the models. And so it wouldn't have given them the guidance to say, you need to investigate what's going on. You need to take some action and improve your quality work, and how can we do that? How can we help you do that? So this really showed the group that we needed to do this during the trial. So for the 36 months of the trial, we did in fact maintain the national model in the background, which turned out to be very fortuitous because the study started in fall of 2019. And so we were able to keep their model and the tool that was being shown to these cath labs up to date throughout the pandemic. Of course, they were not all running the whole time, but when they came back up, the model was still there, ready to help them out. And then here at Vanderbilt, not here, because we're in Michigan, but over at Vanderbilt, we're currently working to integrate these methods into our larger algorithmic vigilance platform. And that's being driven by our chair, Peter Emby, where not just we're going to monitor performance, but we're also going to monitor impact and the inputs, so that if our updating methods that we're doing in the background aren't able to restore performance for some reason, because that can absolutely happen, we'll have visualizations and insights to help technical and clinical teams correct what might be going on that's not necessarily fixable in the data on its own. And that brings me to a point that I just want to highlight for all of us, which is that while I've been talking about data-driven learning prediction systems, they're really going to require a much more comprehensive approach, because not everything is going to be caught by the data-driven approaches, and not everything needs to be caught by them, right? So we can do things that are preventive. We can just build fundamentally more stable models, and there's a lot of research teams working on how we can do that. But even if we have more stable models, we don't want to just assume that they're going to be always safe and always working as expected. So if we have technical and clinical teams that have a sense of the landscape of upcoming change and the situational awareness to know what models that we're running, of the many models that will hopefully be running in the background, they can go ahead and get those corrections made, get them fixed before they start to break, right? That takes a lot of resources, but it's an important piece that we can preemptively keep our models working. And then, of course, the responsive data-driven methods that I've been talking about. But even those are going to miss some things. So sometimes your model, the accuracy might not be changing, but its impact is changing because suddenly the workflow has changed and we're not delivering it to the right person, or we're not delivering in the right setting. And that's not going to be obvious to our data-driven methods. And so a true learning prediction system is going to have to be reactive to end users. And they're letting us know when something's not working. I do want to say, of course, we want to minimize that as much as possible, because once someone reports that it's not working, you've lost that person's trust and all of the people who are just quietly ignoring you now. And so if we need the whole system, but if we can get most of the problems corrected before it ends up in our user's lap, that's what we want to be doing. And in order to do that, we do need a lot more institutional commitment and governance and policy and leadership to really push for the work and the effort and the resources that we need to proactively keep our models working, and not just implement them and say, yay, we implemented a model. And that requires new skills and competencies, not just for our technical teams, but also for our clinical teams and clinical champions who can say, if we go to them and say, this model's not working and we don't know why, they would have the understanding to be able to look at some visualization tools and help us understand how we can improve their models. And then, of course, there's really interesting and challenging ethical implications of a learning prediction system. We're doing some exploratory work now, looking at, population level performance drift isn't necessarily happening the same way in all of our subpopulations. And there are really challenging problems if we're seeing differential performance drift and if updating is not working the same way for all of those populations. And that's going to require some larger rethinking about how we guide the decisions we make in our implementation designs and in our monitoring designs. But I will say I'm still hopeful. I don't want to end on a sad note. I think there's a lot we can do, and there's a lot more acknowledgement that we need to be doing something, and that's the first step to us actually getting these things up and running. So I'm happy to take questions now or later, whatever works for everyone.
Let's do like 2 questions now.
Sure.
Great presentation, thank you. Very on point. I have a question about third-party vendors in the space. So do you use anything at Vanderbilt, or what do you think of the companies that are coming in saying, we can monitor all of your AI models, we can do all these things that you can't do on your own?
So we have been looking at third-party, but we haven't implemented them yet. A lot of the ones that we've looked at, the aspects of performance that they have focused on are not quite tailored to what in the healthcare space we might be most interested in monitoring. And so figuring out where we can customize them to work with what we're interested in terms of how our models are doing and their impact and their accuracy and how those all balance together. And so right now we're mostly doing in-house until we can kind of figure out what we want to do, but we are exploring some of those options.
Interested to hear what specifically do you think they're missing, or are they like?
So a lot of them, the first few that we looked at, they were more interested in sort of, and Epic's, I'm not going to say anything bad about Epic, vendors have traditionally focused more on, are we consistently delivering the predictions? And that's not really the same question. We're more interested in the accuracy and the impact of those predictions, and that's a little bit of a different question. It's not just when you have the prediction, but down the road we need to still keep that feedback coming back. And that's the part that we're still trying to find the right source to give us that.
The equity question. So the kind of downstream, this model does not calibrate well in different subpopulations question, I agree, kind of just pointing this out, raises concerns about what we're doing at the beginning in terms of model design and discovery, right? So I think that's a very interesting point, just gonna bring it up again, because I think that's the issue. And we've discovered this too, and I'm gonna say this in my talk, but there's basic things that we do in medicine, basic models, point-based systems that when you apply them to different populations, we've 20 years later realized, well, that doesn't work so well for everybody. So I think that has to be upfront and front and center for going forward, basically.
Yeah, and all of the more recent best practices, including the updated tripod for AI, all mention that we need to be thinking about fairness and bias when we're deciding if a model should be implemented. But we haven't taken that next leap of what if it changes over time? And clearly, if performance is changing over time, it makes sense that algorithmic fairness would be as well.